Good afternoon again. We are back in the session. If you remember, as we ended the previous session, we were discussing tossing of coins. So here I've got a coin and I'm going to spin it a little bit and you will notice it picks up something. In this case, it turned out to be a head. I tried to do the same thing again. I'll try to turn it in a different, my God, it turned out to be a tail. Just a chance. Now, different types of events, such as tossing a coin or rolling a dice, any of these things, different events, they have different characteristics. Let's try to understand what different types of characteristics are there if these events occur in real life. Unless we understand that, we won't be able to combine, we won't be able to calculate what we call the probabilities correctly. That will not be able to do. Let's see how we do that. I have two simple categories. I have one kind of event which I call mutually exclusive event, and I have another set of events which I call independent events. And these are shown on the slide here. Let's try to define what they are. I must start out by saying that the probability of any event would be, it has to be between 0 and 1. You cannot have the probability of an event to be greater than 0, less than 0, or greater than 1. That is just not possible. It has to be restricted between 0 and 1. So, probability is a measure that always stays between 0 and 1. 0 actually means that the event will never occur, and 1 means that the event will always occur, which is clearly not the case with tossing a coin. Okay, now let's take a look at mutually exclusiveness. Two events are said to be mutually exclusive if the occurrence of one precludes, that means prevents the occurrence of the next. And now in this the coin toss situation, the events are going to be either it's a head or it's a tail. So either I have a head or I have a tail. These two events are mutually exclusive. If one happens, if one occurs, the other will not occur. These are mutually exclusive. Okay, then there are other events possible, and those events are called independent events. What are independent events? One independent event could be I toss a coin here and somehow the light goes out. Now, they might have occurred by chance, they might have occurred together, but it does not mean that one is dependent on the other. There are so many events that take place. For example, it's raining in Calcutta and in New York there is a traffic accident. Or like last night there was an earthquake in Andamans, and lo and behold there was a book fair being held in Delhi. There is no, these two events have absolutely nothing to do with each other. They are totally independent of each other. So what we are talking about, there are two types of events, and these determine basically, are we going to add the probabilities, are we going to multiply them, or whatever we will do. What is an experiment? An experiment actually is something that produces an outcome. For example, flipping a coin is an experiment. Flipping a coin 3 times is also an experiment. Any experiment will produce an outcome. And generally speaking, experiments are driven by many different factors, so we call them random experiments. Rolling a die is similarly an experiment because it's got outcomes and the outcomes are random. And drawing a sample of size 50 of products, it could be for example pens produced by a factory, by a machine, drawing a sample of size 50 from a full range of production, full day's production. That also is the example of an experiment. What is a trial? A trial is the physical action. The trial is, for example, in this case, when I've got this coin in my hand, one trial is flip the coin and let the coin fall somewhere and look at the output. That is a trial. And it turns out that this trial may be different. The outcome of this trial may be different from the outcome of another trial. Again, I flip it and there is some other outcome there. And I flip it again. Each of these are trials. Each of these are trials. So trials lead to outcomes. Trials are the steps involved in producing the output. If you look at all the outputs together, the set that comprises all the different outputs, that total set is called the sample space. So here in the diagram, I've got this little blue area, which is like a little lake there. This is actually, outcomes are inside and the set itself is the sample space. No outcomes can be outside the sample space. I define the sample space in such a way that it comprises all the different outcomes. So, there are lots of examples given here and the outcomes are there. For example, those are given here in this particular instance. I assign now probabilities to events. For example, we know from experience the chance of the event being a head is 0.5. The chance of it being tail is again 0.5. These are probabilities that have been assigned to those events. Again, what is the rule by which I will be assigning these probabilities? The assigned probability value must be between 0 and 1, number 1. 0 will imply that the event will never occur. 1 will imply that it will always occur. And of course, many events are never certain or never totally uncertain. Therefore, they will have some value of p, probability, that will be between 0 and 1. What types of estimates we have for probabilities? There is something called the objective estimate of probability. And this is based on relative frequency. So, for example, somebody again came along with this coin and he had this coin in his hand and he wanted to make sure this coin is what was used in betting between me and him. He said, I am going to bet you 100 rupees based on the results of this one outcome. I have to now then decide, should I play with this coin or should I tell him, no, there is a big chance of losing money, therefore I am not going to be playing. And before that I have to find out basically, is this a fair coin? For that what I do, I toss it 200 times and I count the actual number of heads found. Let's say the actual number of heads found in 200 trials turns out to be 85, which actually means I am less likely to find a head than a tail when it comes to tossing using this particular coin. Here I have got frequency. What is this? It's 87 divided by 200. And that in your thing, if you wanted to just do the exact calculation, you would say 87 divided by 200. That will turn out to be 0.435. That is the probability of, a coin of the type that has got this defect giving you a head. It's only, we'll call it 0.435. That is the probability for finding a head with a defective coin. Now, let's say I take a different situation, in which case I go by belief. And most of us, we are used to the rupee coin. And we know that the rupee coin is reasonably balanced because we may have flipped it a few times. We might have actually seen what happens. And what we found is if we do it 200 times, nearly 100 times it will be head, nearly 100 times it will be tail. And therefore, I can make a subjective assessment there. I can probably say, well, this coin is fair, it's 50-50. This is now based on belief. Belief is quite different from actual counting. Actual counting of heads in a number of trials, that's going to give me what we call an objective estimate of probability. And based on my belief, if I give a number, that's going to be subjective estimate of probability. Both are used. It all depends on when we are able to find a number and we are not able to find a number based on our experience. Let's try to see a situation when we have the odds given to us, and the odds are given to us by observing again. And in this case, let's say the odd is in Hong Kong, as you probably know, like in Bombay, we got a racetrack. In Hong Kong also there is a racetrack. And there are various horses, and the horses are named Beijing, Shanghai, Hong Kong, and so on. And those are raced in the evening. And there is a particular horse, and people are saying that the odds of that particular horse winning the Hong Kong Derby is 9-2. 9-2 basically means if the horse ran a total of 11 times, 9 times, the chances are that 9 times out of those 11 times he is going to win. Now, if the odds are given as 9.2 and somebody says, please tell me what the probability is, I just did that for you. And it's sort of like this. I have here the probability of this particular horse winning. This 9 is the chance of winning divided by the total number of trial chances available, which is 9 plus 2. So 9 divided by 11, which turns out to be 0.82. That is the likelihood, that is the probability of this horse, which is named Shanghai, winning the Derby. This is one particular example. I can have another example, and I'm going to bring another example now for you. And it goes like this. I have, as you see in the slide, I have events which are O1, O2, O3, O4 and so on and so forth. These are going to be various outcomes, k different outcomes that occur when the event A occurs. Any of these occurring, O1, O2, O3, O4, any of them occurring would signify that the event A has occurred. If that is so, for example, I could have a number of boys walking to the room. I would have a number of boys walking to the room, and each of them is a distinct person. So I call a particular name and somebody walks in. Then I say, okay, the next person, and so on. If only boys enter, then the event that a male has entered this room, that event has actually occurred if any boy walks in. If by chance a girl walks in, of course the event that a male person has entered the room, that event will not have occurred. Now, if there are there are k boys standing outside, what is the chance of my event A occurring when A is the event that actually says a male has entered the room? That's going to be the chance of any one of those k boys entering. And therefore, to be able to do that, I add the probabilities of the first person entering, first boy entering, plus the second boy. And remember, these are all disjoint. These are all disjoint. That means there is nothing common between boy 1 and boy 2. In fact, let's take a look at an example. The number on the license plate is a digit that is between 0 and 9. Just a single number they are looking at, and that is between 0 and 9. How many different possibilities are there? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 possibilities are there. What is the probability that the first digit is 3? You've got strings of numbers on the license plate. The very first one could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the chance that the first digit is 3? You can see very easily that the first digit turns out to be 1 divided by 10, because there is 1/10 chance. There's 1/10 probability that the number 3 would have appeared in the first position. Now suppose I ask the second question, which is what is the probability that the first digit is less than 4? Less than 4. That means 4, 5, 6, 7, 8, 9, these are excluded. So what are the digits that could lead to the first number that is less than 4? It could be, if you see the answer here, it could be that the number is 0, or it is 1, or it is 2, or it is 3. Now, because there are 10 numbers, any one of them would have the probability of appearing at 1 by 10, and there are 4 such events and they are all independent. And it turns out in that case I can add their probability, and the probability of the first digit to be less than 4 is going to be then 0.4. Quite easy to work it out. But I did use some rules, and one of the rules I used here was when the events are disjoint, then for them to occur together, and we have to look at that compound event now. The first event occurs and the second event and the third event and so on. I'll have to add the probabilities, and this is what I did in the other case. Then there are certain things which are called compound events, and the simplest example of a compound event is the event A and its complement. Like you look at the yellow area, or kind of the greenish yellow area right in the middle, which is the event A. That is the space. If any outcome appears inside, I'll say event A has occurred. If any event occurs that is not inside A, I'll say the complement of A has occurred, or A bar has occurred. The sample space is the set of all the outcomes. Some are inside A and some are outside A. And therefore, the probability of the event A occurring plus the probability of the event A bar occurring, if we add these two, it should turn out to be 1, because then nothing else is possible. Either it will be A or it will be A bar, and the sum total of this is going to be 1. This is the additive law of probability. And what is distinct about A and A bar? They are disjoint. In fact, if this is the story, then of course I can find probability of A bar, which is simply going to be 1 minus PA. If I know PA, if I know this probability, I can find the complement, the probability of its complement, which is A, occurring. And let's take an example, a very simple example. And the example is this: the chance of getting a computer working is 70%. 0.7 is the probability of a computer working. And then what am I talking about? I am talking about the chance of my getting a defective computer. Now notice, working computer and defective computer, they are complements of each other. If the chance of the computer working is 0.7, obviously the chance of the computer not working is 1 minus 0.7, which is equal to 0.3, which is what we have shown here. If you look at the outcome here, this answer here, it actually tells you that now the complement has occurred. So I've got a defective computer in my hand. This is like, let's take a look at some of these others also. Unions and intersections of two events. Unions are those conditions when the outcome can be either in this set A, or it can be in the other set B. Then I say, if the event has occurred in the union of A and B, it has either occurred here or occurred here. So anything that appears either within A or within B will belong to what we call the union of A and B. Notice here, A union B. I put my cursor right there. A union B is basically any outcome that falls either in A or in B. So I actually designate that by saying the outcome is actually either in A or in B. Obviously, it could be in both. That also is all right. When I do that, I've worked out what we call the union of two events. What about the intersection of two events? It's going to be only those outcomes that come right in the middle. That means they belong to A and they also belong to B. So these events here, which are inside A and B, these are going to be now at the intersection of A and B. A and B are two different events. A and B, A is the result of certain outcomes. Certain outcomes together they constitute A, and certain outcomes together again they will constitute B. A and B together, they form the union, and whatever is common between A and B, that forms the intersection of A and B. And that's what we have right in the middle. What we have in the middle here is basically the intersection. These elements belong to A and also they belong to B. Now we come to what we call the law of adding probabilities, and this is very, very important. It's very important for us to appreciate that this is now the beginning of building a kind of a calculus, or kind of an adding rule, multiplying rule, subtracting rule, and so on with probabilities. And these probabilities cannot be added and subtracted like numbers, because they are not numbers. They have the number as appearance, but in themselves they are not counts, they are chances. They are the odds, they are the chances. This is a very, very important rule. The first law is called the additive law of probability. It says the probability of A union B is equal to whatever belongs to A, the chance of that, which is PA, and whatever belongs to B is now union. Union is therefore either in A or in B. That way it will work. But if I just added PA and PB, I'll be adding this whole area and also adding this whole area. Then this area will come once in A and again it will come once in B. Therefore, it will become actually something that is more than A plus B. So what we have to do is, if we have to really look at the probability of A union B, we have to subtract this area, which has now been counted twice. Once it has been counted using A, when I'm counting PA, it is there. A union B, A intersection B is already in A, and A intersection B is also in B. Therefore, I have to take it out. It's been counted twice when I write this expression here. When I write this expression here, PA plus PB, it's already got this guy, this A intersection B counted twice within them. Therefore, I subtracted once. So what is the law now? It says probability of A union B is equal to PA plus PB minus the intersection of A and B, minus the probability of intersection of A and B. That is the additive law. And let's take an example. At Cornell, this is a school where the first year students, they must take chemistry and math. This is a requirement for all first year students entering Cornell. Suppose 15% fail in chemistry. These kids apparently they came from not such a strong high school, and they managed to fail in chemistry. And 12% managed to fail in math. So some people failed in chemistry and some people failed in math. But there were 5% that failed in both. So here I've got this A situation. Situation A is failing in chemistry. Situation B is failing in math. And some people, they failed both in math and also chemistry. If this is so, if the numbers are given like this, suppose a first year student is selected at random. I walk in there and I ask someone to stand up. And I ask him, what about your performance in the school? What do you think is the chance that the student selected would have failed in at least one of the courses? That means he would have failed at least in either in math or in chemistry, or perhaps in both math and chemistry. Let's try to see how we calculate that. Notice here, we are given that the probability that the person fails in chemistry is 0.15. We are also given that the probability that the person fails in math is 0.12. And the fact that the student can fail in chemistry and also in math is 0.05. That is given to us. And what we are talking about is the student failing in any of these courses, either in math or in chemistry or both. So for that, what I need to do is I need to work out the union of all these things. How do I work it out? I write this formula there. At least one really means either in math or in C, of course, or in both. So I do this union. I do math union chemistry. I end up with probability of math plus the probability of chemistry minus the probability of M intersection C. And this I find out because these numbers are given there. I find 0.15 plus 0.12 minus 0.05, and the answer turns out to be 0.22. That is the probability that the student would have failed in at least one of the two courses. He could have failed in both, and that's also counted within this incident. So this is like how I calculate unions. Let's move on here. There's something called mutually exclusive events, and these are tricky events. What kind of events are these? It turns out mutually exclusive events, they preclude the occurrence of the other one. Remember the coin toss experiment. In the coin toss experiment, head and tail, these outcomes are mutually exclusive. So if the event head occurs, tail will not occur. Or if the event tail occurs, head will not occur. This is something that actually is controlled by the nature of the process and the nature of the object that we are looking at and how we are observing things. So there are many examples of mutually exclusive events. When the two can't be even partially intersecting. If that is so, if you look at the union, if I have to say that the probability, I tossed the coins a few times and I wanted to add up the probability of either A or B, either head or tail. If I just wanted to do that, how would I do that? I'd do it by the union formula. Because A and B basically says A or B. If there is nothing between them, notice here there is nothing between them. That means the intersection is 0. It is the same old formula that we were using earlier. But there is nothing inside the section that is common between A and B. It has got null. Null means nothing is there inside that. If that is so, my old formula, which was written as this formula, A union B, and I had here A union B given as PA plus PB minus P intersection C. If A and B are disjoint, if A and B are mutually exclusive, which is like in this case, there is nothing common between them, the expression will then turn out to be P A union B, which is like A or B. It will be PA plus PB. That would be the probability calculation for this. So for mutually exclusive events, I have this simple addition. Let's take a look at two independent events. Can they occur together? Yes, indeed, two independent events can occur together. Like there was an earthquake here yesterday. At night there was an earthquake. And of course, in Delhi they opened some fair. That event also took place. So there was a certain probability that it could have occurred yesterday or any other time. It turns out if I'm looking at these two events, the occurrence of the earthquake and also the occurrence of the opening of the fair in Delhi, these are independent events. They did not influence each other in any way. One could have occurred on its own, the other could have occurred on its own. There is no real dependency between them. If that is so, if I'm looking at their joint occurrence, this word is very important. The word is called joint occurrence. Joint occurrence. This is a very important thing, and joint occurrences can occur. Certainly events can be independent, but they can occur together. It's a coincidence, but they can occur together, and therefore there is a joint probability also possible. Like for example, there are a lot of examples given here. Flip a coin twice. So I take a coin, again I take a coin and I flip it twice. What is the probability of observing two heads? I toss the same coin twice. Now the first toss has nothing to do with the second toss. And the second toss has nothing to do with the outcome of the first toss. Remember this. And then the event that I am interested in is observing two heads. That means the first occurrence is a head and also the second occurrence is a head. Both the first and the second, they have the same outcome. But they are independent, believe me. So what is the chance of their occurring together? It will be the multiplication of the probability of finding head in the first toss and the probability of there being a head in the second toss. And there, of course, I'll be doing this multiplication. I'll be doing probability A intersection B. And that will turn out to be probability A and B in probability language. It will be PA times PB. So when I did the calculation, I will just describe some of the events here. One event turns out to be like this. What is the probability of observing two heads? And I've written it here, and I hope you can get close to the screen and read them. This is going to be half for the first being head, first toss being head, and half for the second toss being head, and the multiplication of the two turns out to be 1 by 4. That is the joint probability of my finding a head in the first toss and a head in the second toss. Now let's look at the second event. Flip a coin twice, and you can read the event very clearly when you come down to your slide here. The second question says flip a coin twice. What is the probability of getting a head and then a tail? Now I'm talking about getting a head in the first and a tail in the second. Now this is occurring in a very strange way. It turns out I've got a head in the first toss, which is 1 by half, and a tail in the second toss, which is 1 minus 1 by half. And by chance it also happens to be 1 by 4. 1 by half multiplied by 1 by half, and don't confuse this one with the previous 1 by 4 that we had. This is the probability of this particular event, which is like getting a head in the first toss and a tail in the second toss. This will not be so if the coins were asymmetric. If the coins did not give you 50-50 chance of getting a head, the numbers here would be different. Okay, it also says here, I tossed it twice. What is the chance of my getting one head? One head. How will I get one head? The first toss could be a head and the second toss could be a tail. Then I'll get one head. Or the first toss could be a tail and the second toss could be a head. This is the other one. So I've got two ways to get one head. Head and tail or tail and head. The first one is head and tail. I already calculated the probability for that. Head and a tail, that's 1 by 4. And a tail and a head, it turns out to have the same probability. If that is so, I have 1/4 plus 1/4, and my answer turns out to be half. So half is the probability of doing two tosses and finding at least one head. Find exactly one head. Okay, then let's take a look at the third example. There are 3 computers ordered. 3 computers have been ordered, and the probability of any one of them working being in a working state, that means I boot it and it boots up, it's 0.7. Now what kind of event is this? Think of this. 3 separate computers have been installed. Do they influence each other? They don't. Unless, of course, the power supply goes off or something. And if there is a common power supply, then of course all of them will not work. But suppose they have been purchased in a way, they come from different places perhaps, and the number we are given is 0.7 is the probability of any one of them being defective. What is the chance that all 3 will work? These are independent events. The first one working, the probability of the first one working is 0.7 given to us. The chance of the second computer working is also 0.7 taken by itself, again given to us. The chance of the third one working is also 0.7 given to us. Therefore, in an event when all 3 are working, and these are independent events, is going to be 0.7 multiplied by 0.7 multiplied by 0.7, which is what I have if you look at the bottom of the sheet here. If you look at the bottom of the sheet here, I've got 0.7 that is for the first computer to be working, 0.7 for the second computer to be working, and 0.7 for the third computer to be working. And if I put my calculator here, I do 0.7 multiplied by 0.7 multiplied by 0.7 equal to, that's 0.343. That's what I get in the answer there. This is like, I could do this because the events were independent. And the rule that I used here is the rule that is right in the middle of the sheet here. Probability of A intersection B when A and B are independent is going to be PA times PB. Again, this is how I begin to multiply different probabilities. This is like one very handy way to multiply different probabilities. Let's keep going here. Let's take a look at some other events also. And for that, what I'll do, I'll define the events slightly differently. And this is going to get slowly more and more complicated. Let's look at the slide. The sample space is such that I'm looking at 3 children being born. And they are being born in the same family. So they have a sequence in which they are being born. And now what is the sample space? What is the set of all the different outcomes? The first child could be a boy or a girl. So for the first child, I already have either a boy or a girl as the possibility for the first child. The second child could again be boy or a girl. The third child could also be a boy and a girl or a girl. No sequence is implied here, just that these 2 possibilities are there for the first child, these 2 for the second, these 2 for the third. So this is like, how many do we have here? I've got 2 multiplied by 2 multiplied by 2. I have a total of 8 different possibilities for my having 3 children, which are like either it could be boy, 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 or boy, boy, girl, or girl, boy, boy, and so on and so forth. If I do that, if you look at the sample space is shown in the screen here. 3 children, I've got the first outcome as, or first possible outcome is boy, boy, boy. Then I've got boy, boy, girl. Then I've got boy, girl, boy. Then I've got boy, girl, girl. I've got girl, boy, boy. I've got girl, boy, girl. Girl, girl, boy, and girl, girl, girl. These are the only possibilities. No other possibilities there. I've exhausted all the possibilities when any one of them can be either a boy or a girl. These are, of course, simple events. And these are actually, they can also be called single events. Now, that was how I defined these events. I defined them to be single, simple, atomic events. That's what they are. So, whatever the family has, the outcome is, it's a simple event that they have a boy, then they have a girl, and then they have a girl again. It's an event. Let's try to see if we could make it more complicated. To try to do that, what we'll have to do is, we'll have to find the probability of a simple event. Remember, we had 8 outcomes. We had a total of 8 combinations possible. If 8 combinations are possible, then any one of them occurring, if they are all equally likely, is 1 divided by the total number of outcomes. So, the total number of outcomes in this case is 8. Therefore, the chance of any of those simple events, boy, boy, girl, or girl, boy, boy, or boy, 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 and so on, any one of them will have the same probability, and that's going to be equal to 1 divided by 8. So that's what I get when I end up with equally likely events. Let's take a look at this. What is the probability of having exactly 3 girls? Which outcome will lead to this? This is going to be G, G, G. And what is the total number of outcomes possible? 8. This is only one outcome that is possible within the total set of 8 outcomes. So it's going to be the odds for my finding G, G, G in the variety of different possibilities of their having 3 children is going to be 1 divided by 8. And what about the probability of exactly 3 boys? Again, it's going to be the same. But let's try to make it more complicated. We can make it more complicated, and we'll slowly try to do that. But in general, actually, when we got events, the events themselves can be a combination of simple events. We can have simple events and they may combine in a way, may end up with more complex events. And the probability of such events is going to be in certain situations the sum of the individual probabilities. And we'll see when this occurs. This is not true all the time, but this will occur. We've got some kids here and the kids are being born. And the probability, we have to work out some of these possibilities and we'll see how we work them out. We'll actually be doing the calculations, so we'll work them out. The probability of their finding or finding exactly 2 girls. Think about this. How will I find exactly 2 girls? What are the possibilities? Let's try to write them down. And I'm going to write them down right here. Exactly 2 girls. So how could I have them? Girl, girl, boy. That's like one outcome that will give me 2 girls. Girl, boy, girl. Boy, girl, girl. Is there any other way I could have 2 girls? Can you think of any other way? When there are 3 kids, is there any other way I could construct a family that will have 2 girls? It's not possible. So it turns out there are 3 different ways I could have GG. Out of how many different possibilities? The total number of possibilities is 8. Therefore, the probability of GG turns out to be 3 divided by 8. And of course, we could be very exact and we could work this out. Let's take a look at similar situations when I get other questions, and we'll try to work out the other questions also. Take a look at, for example, exactly 2 boys. Exactly 2 boys is again the same situation. Boy, boy, girl, boy, girl, boy, or girl, boy, boy. And these are again 3 possibilities only. So therefore, again, the probability for finding 2 boys, exactly 2 boys in a family of 3 kids is going to be 3 divided by 8. At least 2 boys. Now, this is an interesting situation. Here, what are the possibilities? Let's try to work this out. Let's try to construct the picture, then we'll come back and take a look at the situation. I'm looking to find at least 2 boys. And let's try to, at least 2 boys means I could have 2 boys or I could have 3 boys. For 2 boys, I could have boy, boy, girl, boy, girl, boy, girl, boy, boy. And what about 3? How could I have 3? These will give me 2 boys. And what about 3 boys? That happens only if I've got boy, boy, boy. This will give me 3 boys. So together, at least 3 boys, this really implies I've got 2 boys or I've got 3 boys. In this case, what I'll do, I'll work out the probabilities for this. The probability for this turns out to be 3 by 8. And the probability for this turns out to be 1 by 8. When I add them together, I get 4 divided by 8, which is the answer when you look at the answer for this. You end up with 4 divided by 8. So when you're looking at a situation, when you're looking at least 2 boys, you're looking at 2 boys or 3 boys, and you got 4 by 8. At most 2 boys. At most 2 boys. What would be the count of boys here? 2 boys or 1 boy, still it is at most. Is that all? Or what about no boys? So there are 3 possibilities here. 2 boys, 1 boy or no boys. No boys is the easy case, G, G, G. What about 1 boy? Boy, girl, girl, or girl, boy, girl, or girl, girl, boy. This is 1 boy. Then of course you've got the 2 boy situation, because I'm looking at most 2 boys. So that will be boy, boy, girl, girl, boy, boy, or boy, girl, boy. If you add them all up, it turns out to be 7 divided by 8. 7 divided by 8. Then you look at this interesting situation. You should try this. Before you see the answer, you should try this. The probability of finding at least 1 girl. So, of the total outcome that I have here, remember on the sheet here I've got the total, all the different outcomes possible, GGG, GB, GGB and so on and so forth. I have all these guys. How many of these have no girls? Because I should have at least 1 girl. So, to exclude from this those events that lead to no girls. What is that situation? It's B, B, B. That is the only outcome that does not have any girls in it. And what is the chance of that occurring? 1 by 8. Therefore, what is the complement of it, which is the probability of having at least 1 girl? It is 1 minus 1 by 8, which is 7 by 8. And at most 1 girl, and this I leave to you. I leave to you to figure out how I get at most 1 girl. That I'll let's move on here. Think now of students. We'll be doing some more experiments. What kind of events are we going to be looking at now? Now we are going to be doing a little more complicated situation, a little more complicated calculations. Let's start doing these things. What we call, there's something we call the theoretical estimate of probability or the relative frequency estimate of probability. The theoretical estimate basically utilizes all these adding, subtracting, and so on and so forth. And they also utilize certain principles, calculation principles, computation principles. Those are utilized in working out probabilities by theory. And that is the classical approach to finding probability. Then there is, of course, what we call the relative frequency approach to finding probability. And this happens when you count the interesting events, count the occurrence of the interesting events. And this could be done either you observe passively or you do some experiments, and from that you figure out what the frequencies are. You count and find out what the frequencies are. Let's think of a situation when there are kids who are taking a test. So these kids here, they have been asked to take a test, and these tests of course are not very easy tests, so some of them fail the test. Let's say what we've done is we've given them grades. At the end of the test, we've given them grades. And here we are using some actual experiments, actual experience, and therefore we got some real data collected here. If you look at the data collected, it turns out how many students are there? 20 plus 30, that's 50 plus 40, that is 90 plus 10, 100 kids. It turns out that 20 kids scored A, 30 scored B, 40 scored C, and 10 went below C. What is the chance now of scoring a B or better? B or better. What are those events? Take a look at the events. B or better would be scoring A or scoring B. That would be B or better. What is the frequency there? 20 plus 30 divided by the total number, which is 100. So that turns out to be, in this case, to be something very straightforward, 0.5. and I've just written it down, and I've got this little calculation there, and you can really see that the calculation shows you first the total count of all the boys or all the students, and then I've got here scoring B or better. So I've got so many 20% score B, 30% score C. So it turns out overall 50% or 0.5 is the probability of a randomly picked student to have found B, to have found or better, either B or better. That's like this thing. Let's try to make this a little more complicated. So here what did I do? I just used empirical probability. Empirical is based on real data. Whenever I talk about empirical work, I actually mean you actually go out and observe, and you write down the numbers and you do some calculation, you utilize your calculator, and from that you do the calculation. If you're doing this, you're doing empirical work. If you're using it only on the basis of subjectivity or some calculation, you might be using some classical principles. Of course, both approaches could be taken. It all depends on what the situation is like. If there is no way to calculate real data, to observe real data, you may have to do some subjective assessment of what that probability is. Let's take a look at this other problem here. I've constructed what we call a two-way table. And notice here the two-way table is kind of tricky. I have male and female students on one side, and I have students who scored A or who scored less than A shown on the other side. So here this is more like a little matrix. I have one dimension. The rows here are marked male and female, and the columns are marked A and less than A, got less than A. And then here I've got basically the sum total of those who managed to get A and they were male. There are 30 of them, they managed to get A, and 45 could not make A out of males, and for females 60 managed to get A, and 65 of course scored less than A. What I need to do is I need to solve this problem, and I will first pose the problem, of course. And what is the problem? The problem is this: find the probability of a male having, if you randomly approach a student, what is the chance he will be a male? What is the chance he would have scored A? That is probability of PA. A randomly picked student, has he scored A? And what is the chance that he scored A and also he is male? What is that chance? Now, to be able to do that, we need some theory. We'll have to really see. This I could not do just by counting or something. I'll have to work out some theory. Just by doing what we did here, we would not be able to do it. So let's see what kind of theory we utilize. And I'm going to show that to you by showing you first the solution to this. And then we'll explain the theory to you. Notice here, we have the solutions. To approach the solution, the first thing we did was we found out how many total students took the test. It turns out 30 plus 45, a total of 75 male students took the test, and a total of 60 plus 65, 125 females took the test. So the total number of students who took the test is 200. And now if you look at how many got A, that is 110, that's 45 plus 65, they managed to score A out of 200. Those who got less than A, and those who scored A, they were like 30 plus 60, that's 90. 90 managed to get A. So if I now look at this probability here, which I'm trying to find out, probability of A, which is like the probability of a randomly picked student scoring A, that's going to be 90 divided by 200, and that's going to be 0.45. Little calculation there. And now the probability that the randomly picked student is turning out to be a male. What is that? How do I find that? I total up how many males took the test, and what was the total number of students taking the test, and that turns out to be 75 divided by 200. And being how sharp I am with my math, I'll quickly put down 75 divided by 200, and I end up getting 0.375. That is the number. If 0.375 is a probability, that's what I have to put down here. So I've got that thing written down there, 0.375. Now what is the other question? The question is, they scored, somebody randomly picked, was male and also scored A. How do I find that? For that, what I do is I search in this space where the count is available for both of those events. Somebody scored A and also was male, and that turns out to be this space here. This is really the number that meets this condition and also this condition. Note here, this and is given, and is intersection, and that turns out to be, that number turns out to be 30. So again, what I do is I divide 30 by 200, which in this case I don't have to use the calculator. It's a small enough number, that's 0.15. That is the probability of a randomly picked student scoring A and also being male. That is this. So that's how we managed to solve the problem which I showed you on the screen here. I have this event here, and we already have figured out each of these answers. Let's say that you were talking to some people, and these were young students, they really didn't know probability very well, and they were talking a little loosely. And because you are kind of the learned person, they wanted to talk to you in a language that would turn out to be in the language of probability. And they would make this comment, sir, the chance of raining today is minus 10%. What is wrong with this statement? He says the chance of raining today is minus 10%. It's very important for us to realize that probability can never be negative. So there's some, maybe he wanted to say 10%, he wanted it to be low, so he just put that minus there. But be a little careful whenever you get talked to, and if the person is talking probability, the numbers he gives you, these must conform to certain conditions. It's very, very important. Similarly, if somebody comes along and he says, oh sir, the chance of there being rain today is 120%. That means the chance is 1.2. Is that possible? Can probability ever be more than 1? That's not possible. That's not how we have defined probability. So therefore, again, such a statement is not correct, not consistent with the definitions of probability. What about this? The probability of rain or no rain. Whenever I'm calling it or, I'm implying the notion of union. And what about rain and no rain? What kind of events are these? These are disjoint events. In this case, they turn out to be complement of each other. If they are complement of each other, they are sum of the occurrence of the first event and the occurrence of the second event. It must add up to 1, 1.0. So the probability of rain or no rain, the chance of these two occurring, rain occurring, there being rain or there being no rain, the chance of these two when added up, that should equal exactly 1.0. It can never be 90%. Because what happened on the rest of the days? Only two types of days are possible, rainy days or non-rainy days. That's all. There's nothing else beyond rain and no rain. So that's why this statement again is wrong. If I want to remind you of what all things we've been looking at, underneath the paper, underneath my book here, I've been hiding a set of rules. And what are those rules? First of all, the probability of any event that we're talking about must be greater than or equal to 0. That's condition number 1. Condition number 2 is the probability of an event must be again less than or equal to 1. At most it can be equal to 1. So probability of any event must be between 0 and 1. And the probability of the full sample space, which in our case is rain plus no rain. The full sample space, it has got two outcomes. One is rain, the other is no rain. That must be equal to 1. These came from a Russian mathematician, his name is Kolmogorov. And all probability literature is really based on these. If you take away these are like building blocks. If you remove these bricks from underneath the whole building, the whole theory of probability and everything, it's all going to collapse. So you got to make sure whenever you get statements like the ones that are written in red here, whenever you get these statements must be valid against these conditions here. So what are the rules? Let's take a quick look at the rules. If A and B are there, if A and B are two events, then the complement rule says probability of A and the probability of no rain or no A, that's going to be 1. So A is inside the white area there, and not A is the area that is outside A, that is there. This is the complementary rule. And what we have done here, we've used this set theoretic notation. And we define union to be like this: A or B. And the other one is A intersection B, in which case the Venn diagram, these diagrams are called Venn diagrams, it shows what is common between A and B, and that is this intersection. And this is to be very, very clearly stated. You should, whenever you define events, and particularly when we define compound events, you got to make sure you define very clearly, is it a union or is it an intersection? If this is known, then of course, given the probability of A and the probability of B, you can construct what we call the probability of any of these composite events, which is the A union B, which in which case we are saying either A or B will be okay when I'm talking union. And when I'm talking intersection, I'm saying A has occurred and also B has occurred. I'll continue with this as we go along. Thank you very much.